So it's a really pleasure for me to be here with you. It's for the first time to be in Olomouc. When I was invited to present something from my research like 2 months ago, then I was thinking that maybe I should present something what we have new, what is coming from our models. So I prepared abstract, and then last weeks I just found that some of the stuff I'm going to present might be a bit obsolete or already too old. So and I'm going to show you why. So motivation of my research, it's really policy-driven. As you might know, European Commission set out detailed vision to make Europe the first climate neutral in European Green Deal. So there's a set goal for climate neutrality, or to reduce greenhouse gases to 0 by 2050. And the previously set goals, this 40, 30 to 32 targets by 2030, has been just revised in Fit for 55 package, as you might know. It basically means that the greenhouse emission target has been strengthened, and the Commission would like to reduce greenhouse gas emissions by 55% by 2030. And there is, ongoing new legislation, even following the latest geopolitical situation, Russian attack of Ukraine in Repower EU material that was just discussed last week. So, in my research, I would like to contribute to this debate, by modeling energy trajectories or transition in the Czech Republic, and what might be potentially impacts reaching this transition. Of course, climate change mitigation will also bring additional benefits. We also reduce other pollutants like SOx, NOx, particulate matters, and these reductions in emissions will bring additional benefits, like improving health. I acknowledge that, but I'm not going to present this, even though you can find these estimates in our papers. So what we are using in our modeling exercise, so we have a couple of models. We have macro structural models like CGE, macroeconometric model, but what I'm going right now to present, it's based on energy system optimization model TIMES. So it's bottom-up, technology-rich model. In that, whole energy balance and energy system is described. And basically, the model searches for least cost optimal solution to satisfy predefined exogenous energy demand. So what is assumed in this kind of modeling? What will be the price of emission allowances? What will be prices of fuels, biomass, investment costs of new technologies, and then after you run the model, then endogenously what you can derive, it's a new technology mix, new fuel mix, emissions, energy use, and since we have also emissions projected, also external costs avoided. This all is done under certain constraints. You can assume that some fuel is not available, or the amount is only limited under certain level. Or you can also introduce a ban on certain technologies. You would like to have nuclear, or you would like to have nuclear. So this kind of model, it's as I said, is very useful to project how energy system will develop in the long run. We cannot analyze impacts on the economy, like on GDP, employment, and other macroeconomic variables. We cannot also model electricity production in very detailed time resolution, like using dispatch model. So this is a description of our model. We have covered everything what is operating in the Czech Republic, including transport technologies like vehicles. We only don't model agriculture. So time horizon, it covers period until 2050 in 5-year long blocks. We also introduce potentials of renewable energy sources that are just described in state energy policy and so on and so forth. So this is a cost optimization in the model. Basically, we would like to satisfy energy service. So how many degrees of Celsius you heat your home, what is the passenger kilometers, how many electric appliances you have, and basically you need to either use electricity or heat, so there's a first substitution, or you can introduce energy efficient technologies, so you can insulate your home, or you can just, consume gigajoules. And all of this is just done by the model. So basically, the model says how much electricity will be generated, how much electricity will be imported and exported under certain constraints, considering all prices and costs that are just put into the model. So first of all, if you like to analyze trajectories and impacts, you need to define scenarios, because we are scientists, we don't know what the future will be. We can only project some states of how the system will envelop, and then we need to compare the impacts for the two policies, like for reference scenario and the policy counterfactual. So these are our scenarios. One is really BAU, or business as usual, that you just described in state national climate energy policy. And then we have different variants. And when you assume a larger price or higher price of emission allowances, or if you like to really reach zero emissions by 2050, if we assume different assumptions that are just set by European Commission, and so on and so forth. There is one issue that is very specific for the Czech Republic, it's nuclear. You know, the lifetime of nuclear power Dukovany ends in 2036, so we have different assumptions. Either nuclear power will be extended lifetime, or new nuclear block will be built, or nothing will happen, and only model we say, or will optimize the system whether new nuclear power will be installed or not. One important caveat or note, that we don't assume any imports of biomass, biofuels, and hydrogen. You know, you might see different modeling, and they just assume, we will just import 20% of hydrogen for Germany. But we know that every country will be just, will need to reach its target, so they will be really fight for hydrogen and biomass and other sources that are carbon zero, that they have no emissions. So we don't assume anything. We assume that there is a zero. Everything, all hydrogen need to be generated domestically in the Czech Republic. So that's our assumptions. And here you can see the prices of emission allowances. So we have different scenarios. So the price could go up to 200. Before it was, 15 euro per ton of CO2. You can also see prices of oil, gas, and coal. I will make a note in 5 minutes, because this is very important, because we have a problem here. So here you can see the results. So the first very clear result is that Czech Republic is not able to reach zero. So we can see we end up with about 20 million tons of CO2. So it means for us, one first message is that we need to do more than we have been expecting in our modeling exercise. So you can see reductions for ETS sector, for trading, and for non-ETS sector, there's basically transport and buildings or households. Through the measures, and since the prices are going up, primary energy demand is going down much more, because there are more renewable resources, and final energy demand, basically consumption by final users, is also going down, but not so much as final demand. This is a clear result, and this is mainly due to energy savings or energy efficiency that are introduced in the system. So primary energy use by fuel, you can see very clear decrease in total energy use. There is a natural gas that is going up. You can see some imports in violet on very bottom that will disappear after 2040. You can see that the nuclear for some scenarios is reduced. It means the nuclear power is not economically rational or competitive solution, or because other sources are able to generate electricity with lower costs. You can see these white parts, heat pumps. So the electrification is more profound in energy system of the Czech Republic. Here is the same picture, but for final energy demand. You can see that electricity, the share of electricity is really going up. Also, relatively speaking, natural gas is going up. We have a bit hydrogen by blue, and biomass is also increasing their share, and of course renewables. So in industry still we need to consume some coal in technological processes, to produce steel, cement, and other materials. So this is a big problem to reach zero. For that reason, we need to have technologies that produce negative emissions. If we capture and store carbon, especially from biotechnologies or from biomass. Through that, we can really have a negative balance. So this is electricity consumption by sectors. Transport is going up due to electrification. We have battery electric cars, and in other sectors very similar. So new installed capacities, you can see by technologies, these are increments by 5 years periods. There's a lot of solar, wind, coming up, especially after 2035. If we look at cumulative number, so we can see huge installations of solar with this yellow, but also natural gas. Natural gas, on very right is natural gas with CCS, so this is carbon capture storage. On very left, on second in order, it's biomass with CCS. So we have some technologies with carbon capture and storage. So of course this will cost something. So we have investment costs. This is for power and cogeneration of electricity and heat, and by technology. So this is quite important information for others if they would like, to maybe subsidize or support certain technologies and to maybe boost some of the technologies to penetrate the system more, to reach maybe more stringent target. These are overall costs of the system, not only power and cogeneration. Green part are investment required, to replace old vehicle stock, so basically vehicles. So you see that power does not represent the largest sector in terms of investment. So another message is that we would need to invest in some sector anyway, because we cannot really drive our car for 50 years, at least an average person cannot do that. So in 10, 20 years, we need to buy new cars anyways. So what we should do, we should really look at the increments if we compare to scenarios. So this is just the same picture. Now this is again for whole balance, investment costs, but now I express it as a difference compared to business as usual or reference. So many, present these huge numbers that there are really billions and billions Czech crowns needed to reach these targets, but they forget to say that we cannot really use technologies for forever. These technologies need to be really replaced. So what we need to do really to compare costs for two scenarios, when we do nothing, or when we just keep going without reaching carbon targets, and with more stringent policy. So now you can see the differences. Of course, differences are huge for some scenarios. Still we are talking about billions, but we have also some savings for some scenarios. Like for Bau Zero, just because already some investment has been done before. I mean, to 2030. So we should have this picture really to model the system in long run and compare the costs, not for next 5 years, but for 50 years or let's say 35 years, and compare the costs for different scenarios. So here we have annualized costs, basically average cost for year. So we have investment cost by blue, investment costs like subsidy coming from government in red. Basically here we have zeros. We have expenditures on fuels by green, expenditures on emission trading for allowances in violet, fixed cost, variable cost, and green bonuses. So we have this composition of the costs to get that picture of what we might expect in this particular sector, and then in the economy. And again, we have the differences now. You can see the differences up to order of, let's say, it's 100 of billions Czech crowns a year. So it's something, but it's not terribly a lot that would kill the system. And of course, we have also negative contributions. So this is again the same picture as I presented 10 minutes ago. What are the impacts on greenhouse gas emissions in the Czech Republic by 2050 by sector? You can see on the very right that we have something green under zero. These are actually negative emissions achieved just thanks to carbon capture storage technologies, especially installed on biomass. Okay, so grayish, the gray one, it's agriculture. We have problem here. We are not able to model anything because we just exogenously assumed how it's going on in agriculture, because the Czech Ministry of Agriculture is the only one who assumes that the emissions will be just increasing over time because they wish that the number of cattle, cows, pigs, and other animals should just grow for some reasons. So, and we know that quite a lot of greenhouse gas emissions are just produced by this particular sector. So this is another message. If we really like to reach zero, we need to really do something in our agriculture, not only to introduce some special techniques for farming, but maybe also to think how to motivate people to change lifestyle, maybe diets. You know, Czechs are really meat eaters. We just conducted another experiments in that we, you know, asked people whether they under which conditions they would change their behavior and lifestyle with changing price, showing what are the cardiovascular disease associated with that consumption. And we found that there is some potential, but of course, this need to be better communicated and maybe provide some subsidies on fruits and vegetables and really some meat tax on meat, because there is really overconsumption of meat causing a lot of adverse health effects, not only climate change. Okay, that's it. That's it. What are the emissions of greenhouse gases? So, as I said, that it might be a bit obsolete because, you know, Europe is now in the war. Russia attacked Ukraine, and there are many consequences on energy market in the world, especially we really don't know. There are a lot of uncertainties how it will be with imports of natural gas. And here you can see Czech Republic is heavily dependent on gas imported for Russia. So basically we are only red with Hungary. Last year it was 97% of gas that was consumed in the Czech Republic originated from Russia. Okay, so here is our assumption. So we assume that the price of natural gas will be about 15-20 euro per megawatt hour. If you look on very bottom, there is just a recent price, or let's say price for last 6 months. Now natural gas costs 100-120 euro per megawatt hour. So it's 6 times more. We don't know whether there will be embargo, whether the availability of gas will be lowered. You have a data on imports of EU 27, so it's about 40%, 160 billion cubic meters. LNG, you know, Biden agreed to share their LNG with us, with Europe, but it's only 15 BCM. And as I said, Czech Republic is heavily dependent on that. If you look at the right bottom, you can see the projections for natural gas that is about 60 euros per megawatt hour. So now what we are doing right now, because we are just presenting this research for Ministry of Industry and Environment, we are just running again our models times with these new assumptions of much higher price of natural gas and maybe some constraints on natural gas availability. So far, we don't have results, but just I just said, you know, it's just assumed that the gas will be here for the price that is just presented in the table on the bottom. Of course, these changes in energy sector will also imply some cost on the economy. As I said, we cannot use times model, but we have another model like CGE, computable general equilibrium model, and macroeconometric model, E3ME, that we are running with Cambridge Econometrics together. It's post-Keynesian model. It's always very good to understand what these models, how they are built, you know, because these post-Keynesian models, they just assume there is some capacity in the economy that is not used, basically, that you always have some inefficiencies in the system that might be used if there is some push. So there is no general equilibrium, so there are some adjustment in the system just because, you know, some capacities are not used. So we run this model for these 3 different types of scenarios. So when a new nuclear power plant will be installed, you know, immediately, and they will replace Dukovany that are going to be closed. Or there will be some delay, like 10 years, when new nuclear power will be built. And another scenario, it's just Dukovany will be just extended their lifetime. Then another scenario is ETS. You know, what will be the impact if price of allowances is about 87, 116 by 2030 and around 180 in 2050 on ETS sector and emissions and in the economy. And the third one is CBAM. CBAM is Carbon Border Adjustment Mechanism. Basically, it's a carbon tax on imports. So basically, this is a mechanism how to avoid carbon leakage and make EU companies competitive. You know, they should have equal conditions like companies in India, China, Brazil, and Russia. So this is a CBAM. So we model these three animals here, and so basically what we find that how nuclear power will be installed really will affect emissions. We also find that ETS strength reduce emissions much more, but we also what we found that CBAM will not reduce emissions at the EU, okay? Basically because if you have CBAM, you get new revenues that need to be recycled or used. And actually we assume that we reduce other taxes like VAT and labor tax to have revenue neutral policy. So of course emissions will be reduced abroad. So I just show you how is it with GDP. For nuclear, you cannot see barely nothing. It's very close to zero. So it's only like demand shock that will increase slightly GDP. But ETS, just because of unused capacities and some stimulus, investment stimulus, at least according to this model, the expectation is that GDP will be increased up to 2%. So the impact is positive. Be careful, this is always relative to some business as usual. And for us, it's a scenario without ETS and if Dukovany will be extended. We don't know what GDP will be. Yes, right? We are economists, we can only compare. Okay, and CBAM will increase GDP more because we have additional money in the system, right? From revenue recycling, and also imports will be more expensive, maybe more production will be done within the EU. But overall, running this globally, the globe, we get positive impacts on the GDP. Employment just follows GDP growth, but only it's a bit delayed by 1 year, and in magnitude is only half. And we have also impact of prices. So just look closer on transport. Maybe it's also important to discuss that. As you can see on the bottom, we have final demand for transportation. So the red, it's diesel is going down. Pinky, it's petrol. It's also going down. And the violet in the middle, it's electricity, okay? So we are going to electrify transport because we will have battery electric cars. You can see here our modeling that is based on stock flow model that is incorporated into Times model. What is the vehicle fleet by fuel? And definitely you can see that in the stock, battery electric cars are going up, so the share is going up. Even now we have some electric cars, like 5,000. But remember that new registrations only represent like 5% or 7% of the stock. It requires really time when the flows will be represented in the stock. Yeah. So that's it. What we have here, what our model predicted. So now about some myth. You know, there are some arguments that battery electric cars are not really good because they are charged by electricity that is produced by dirty fuels like coal in the Czech Republic. It's true. Average carbon intensity is 540 grams CO2 per kilowatt hour. That implies 100 grams CO2 per kilometer. But what we should really consider is not carbon intensity today, but when battery electric cars will be driving on the roads, maybe in 10, 15 years. So for that, you can use the results from our model, from energy system model. In that, we projected what will be carbon intensity in 5, 10, 15, and other years. And of course, it depends what we will assume about nuclear, about price of allowances, and so forth and so on. So we can see that this comes really 4 years ago when we projected that carbon intensity will fall down by 60–70%. And for 2040, electric car will be much more clean than a conventional car, even if they consume 3 or 4 liters per 100 kilometers. So we should really consider dynamics when we are assessing technologies. So we don't have these numbers yet from newest modeling, but it might be around 100 grams CO2 per kilowatt hour. So what next? Of course, it depends whether people will accept this technology. So what we do in our research, we would like to understand preferences of people or consumers, how they could change their behavior and maybe to buy novel, advanced or low carbon technologies. So what we usually do, we carry discrete choice experiments. So basically we elicit stated preferences within hypothetical contingent scenario. So we basically ask people to choose the best option out of several alternatives. If alternatives are just described by different attributes, like technical characteristics of vehicles, and these attributes, their levels vary. So this is pretty much standard. It's based on random utility model. McFadden got the Nobel Prize for that. And econometrically speaking, you just basically estimate by conditional logit or mixed logit probability to choose alternative X if something. And you can also get marginal willingness to pay, basically how much you are willing to pay for strawberry in your yogurt, or that is in glass, or whether it's really fresh milk or powder milk. So for all of this, you can basically disentangle price into marginal willingness to pay for product attributes. And you can use this information for policy simulation. So we did this, I think like 6 years ago in Poland. So we presented this kind of scenario. This is a choice card. We have a conventional car, hybrid car, plug-in hybrid car, and battery electric car. You have how much it costs, what is the price of technology, what is the driving range, what is the charging time, charging infrastructure, and whether there are other benefits provided by government, like parking in the city for free. Okay, and then we ask people, to choose, and then it's easy. You can just run a model, conditional logit or mixed logit, and you can get utility parameters for each attribute. And from then, you can just decompose, the probability or marginal willingness to pay. Here you can clearly see that, if there is a negative sign, probability is going down. If it's a positive sign, probability is going up. For cost, if technology costs more, probability is going down, and so on and so forth. Here you can see some results. So for driving range, increasing driving range by each additional 100 kilometers, Polish guys are ready to pay 1,300 zlotys or 320 euros. It's not much, but for others it was more important. We find that like free parking and free public transport increases the probability to choose alternative fueled vehicles. Recharging time and availability of fast charging stations is the most important barrier, or this could increase probability to buy these technologies. So you can see the results from our papers. We also replicated the same exercise in the Czech Republic. Now we also added CNG. And we disentangle charging time into slow mode and fast mode charging. You can charge your car within 15 minutes or 20 minutes, like Tesla superchargers, or within 5, 7, 8 hours. So we again run these experiments, and here you can see the typical results. Willingness to pay for improving vehicle characteristics. If recharging or driving range is increased by 100 kilometers in petrol or diesel fueled car, they are not really willing to pay anything, because these cars have already a range of 700, 1,000 kilometers. But it matters if we analyze, willingness to pay for battery electric cars. So then willingness to pay is increasing. If you increase, driving range by 500 kilometers, people are ready to pay more, 100,000 Czech crowns for the technology. And it is the same for operational and maintenance costs. If you reduce the cost, because electricity to running electric car is much cheaper. Yeah, it costs half Czech crown for diesel, especially now it's 3 crowns, so it's 6 times more. So these kind of results you can get. Our results are in line with other research. For policy measures, people really would prefer to have electro installation of subsidies, provided that they can install a charging station at their home. Then willingness to pay and probability are increasing for battery electric cars. For charging time, it was very interesting that they prefer shortening time of slow mode charging, especially from 4 hours to 3 hours or to 2 hours. They don't really paid attention to fast mode charging. Maybe they just thought, you know, they just need to charge a battery electric car when they return from office or from school, and maybe, you know, they just park in the garage and it should be charged in 2 or 3 hours. Okay, my running is time, maybe I'll just finish. So for this information, you can just use in simulation what is the market potential if something happened. You know, if there's a subsidy of 10%, 20%, you know, if electricity costs 0, if electricity costs half, if fuel costs double or triple. You know, you can just use this from your logic and to derive market shares for these 4 or 5 technologies under certain conditions. So this is for driving range, slow mode charging, you know, the better, the higher. It's very clear. Okay, so that's it. But you can also use this kind of exercise for policy acceptability. I'm just skip it. You can just get, you know, the information, how much you are willing to pay for different attributes of policies, and to model what is the probability to accept the policy if this policy is designed in some way. So you can just look at my slides afterwards just to conclude. For the assumptions we used, Czech Republic is not able to achieve this 0 target. We need to do more. Of course, there are some assumptions that need to be discussed. We are able to reach targets on renewable energy sources. That's fine. There's a strong pressure on electrification, not only in transportation, but also in household, because we will be relying more on heat pumps. Nuclear is not economic, rational or competitive solution. If you like to have nuclear, we should understand that this is maybe a suboptimal solution because it costs more. Okay, incremental costs are not huge. 13% of gross fixed capital formation of today, but always we should compare difference with bio. This is my very last slide. So what matters? What is really policy design? What kind of subsidy? Everything is possible to model. We have these tools. Behavior matters. So I really also encourage you to continue in this behavioral stuff, what I really like, maybe even more than energy system modeling, to understand drivers of behavior on how to change lifestyles and habits, and also to analyze policy acceptability, because if people don't like some policy, then policymakers are reluctant to implement this policy. Thank you for your attention.